So from a previous experiment, we have a graph of potential energy versus the separation of a pair of magnets, the specific pair that we're going to use in this experiment. So what do? We set up our beam, we put the extenders on it, and we put one at each end to keep it balanced, and we go to a lot of trouble to balance the system, so there's very little tendency for the system to start rotating if we put it at rest at any of a various number of positions around the circuit. That way we know that the acceleration should be uniform throughout every revolution. Okay, so we put a small magnet on the extender here, put some dominoes here, and a large magnet here. You got to build up some kind of support to put all this stuff, the large magnet and the dominoes on, and it's got to have it at a height that matches the height of where this small magnet's going to be, but that's not too challenging. We release this, take the data we need to infer the average velocity and kinetic energy right after release. Or more importantly, the energy that's dissipated as this thing coasts to rest, analogous to what happened with the car. Now, the difference between this and the car is we don't know what the coefficient of friction is, so we're going to actually determine that in a sense. Okay, so anyhow, so we're also going to time it to rest then, so we know what at least its average angular acceleration is going to be. And you need 3 hands to do this, but if you're really good, you can use 2, and you can work that out, and that'll be in the instructions. Okay, now we want to see what it is that accelerates this system. It is a force, but the acceleration that's produced by force depends on where it's applied. If I want to accelerate this thing here at a certain rate, I've got to push harder than if I want to accelerate it here. Although if I want to accelerate it out here, I've got to keep the push going for greater distance. In other words, I've got to do the same work both ways, in one place with more force and one place with less force and more distance. Okay, anyhow, model. Again, massless rod, length r, mass m here. We apply some net force. Then this thing's going to accelerate on the circular path, and a tangential acceleration, an acceleration in the direction of our motion, if this force remains perpendicular to the rod. Going to accelerate with acceleration F naught over big M. Okay, that's just Newton's second law. Well, then the angular acceleration is going to be this acceleration divided by r, which is F net divided by mr, because if I take this acceleration and divide it by r, I'm going to get an r there. And that's then equal to, little trick here, F net r divided by mr squared. We do that because mr squared is a moment of inertia, and now we have a relationship between F net r, moment of inertia, and angular acceleration. Well, this F net r, okay, well, we can write it. F net r equals I omega. We just rearrange it. If we compare this with Newton's second law, we can see that I takes the place of m, and that makes sense. The greater your moment of inertia, the harder it's going to be to get the thing accelerating. The more kinetic energy it's going to have at a given velocity. Okay? And the more acceleration you want to give it, the more force, the more work you got to do. And F net is then replaced by F net times big R. If you think through why this happens, you can kind of understand why this has to be, but right now just accept it. If we call F net R the torque, using notation tau net for the net torque, tau net equals F net R, then the net torque is what we think of as producing the acceleration of the rotating system. And we call this relationship, well, the relation that we get is, if this is tau net, then this tau net equals I alpha, so right there we have it. We call this Newton's second law for rotation. Tau net on a beam, as a result of friction, is what primarily brings the system to rest. Now that's back to our rotating system, our standard system. So from the moment of inertia and the angular acceleration, which we can measure with the data that we get, we can determine what the net torque is. And that net torque comes primarily from friction in the bearings. Now, having done the experiment, having observed angular velocity versus time, we know that we have a slight upward curvature, slight upward concavity to that graph, so we don't have an absolutely constant angular acceleration. The angular acceleration actually decreases in magnitude. That could be due to friction having some dependence, friction in the bearings having some dependence on velocity. It could also have to do with air resistance, because this thing rotates for several minutes. And air resistance, although it exerts a very small force, will accumulate maybe a significant amount of effect on the acceleration. Okay, and maybe we can even get some clue as to how the net torque might be divided up between torque due to air resistance, which is going to be velocity dependent, and maybe a velocity independent net torque from the bearings. Or maybe torque in the bearings is a little bit velocity dependent, and the air resistance, of course, is velocity dependent. We might find that the air resistance is totally insignificant, and the decelerating torque in the bearings really is dependent on the speed. There are all kinds of conclusions that we could draw if we get good enough data. So there's our experiment. And of course that'll be written up with hopefully clear instructions.